Good morning, good afternoon, and good evening, everyone. I'm absolutely thrilled to welcome you all to the 6th Breathe In Dialogue, organized as part of the Cleaner Air and Better Health Project, also known as the CABH project. These dialogues are envisioned as platform for generating discussions on indoor air quality issues, concerns, and solutions. We will be bringing to you topics under various themes such as regulatory convergence, design and technology, monitoring and management, and occupant awareness. These dialogues are curated by us at Environmental Design Solutions, along with our knowledge partner, the Society for Indoor Environment. Our experts today will be sharing their experiences, research, and perspectives on monitoring and management of indoor air quality. You can look forward to an engaging discussion with our esteemed experts and participate in interactive sessions. Please feel free to use the Q&A function to ask any questions or give any comments. We will also be launching some polls, so do keep an eye on the screens. A little brief about the Cleaner Air and Better Health project. The CABH project is a 5-year project supported by the USAID. It aims to strengthen air pollution mitigation and reduce exposure to air pollution in India. The project is being implemented by a consortium led by the Council on Energy, Environment and Water and includes other social impact advisors, environmental design solutions, enviro-legal defense firm, and vital strategies. I'm Lakshmi, and we are very honored to have our esteemed speakers, Dr. Jelle Laverge from Ghent University, Dr. Chandra Sekhar from National University of Singapore, and Dr. Om Prakash Singh from CAW, along with my colleague, Ms. Nidhi Gupta. Next, I invite Dr. Om Prakash Singh from CAW, who is the Chief of Party of CABH project, to provide us a deeper insight into the project. Over to you, OP.
Thank you, Lakshmi, so much. And I'm thrilled to be part of such a knowledgeable panel here. So I'm just going to talk brief about the Cleaner Air and Better Health project. As Lakshmi rightly mentioned, that this Cleaner Air Better Health project, supported by United States Agency for International Development, USAID, it's a 5-year project and basically aims towards strengthening air pollution mitigation and reduce exposure to air pollution in India. And we do by establishing evidence-based models for better air quality management. And yes, this project is implemented by a consortium which is being led by CEW and supported by USAID, EDS, ELDF, and vital strategies into its different thematic contributions. I just wanted to show you this piece right now. So basically, this is Nai Bharat Ki Nai Hawa. Just to translate in English, it's all about new India's new air or fresh air. So this is a green brass that has been bronze piece that has been developed without any emissions. So this is one of the products that we talk of. I will talk a little bit about it also deeper when I move ahead. So it has almost zero emissions while we produce this element on the ground. How do we take ahead? Actually, when we talk about mitigation and reducing exposure to air pollution, what we basically feel that if we are able to strengthen the mitigation measures, and if we are able to exposure to air pollution, we will have a cleaner air and cleaner environment in place, and this is going to lead to a healthier population in the country. And around this concept, we basically are designed our strategies to work on it. We work on 5 approaches at this moment. One of the approaches that how we can enable monitoring and regulatory reforms as far as in the field of pollution is concerned, because very often we see that it is very difficult to conceptualize these government regulations and orders on ground level, how it can be understood in a simple language for all regulator decision makers and even for the community. One of the challenges that we have already seen that we have a lot of data in place, but then how this data can be used for strategic decision making. This is where also the CABH project is supporting. Third, we are clearly working on clean energy through innovative solutions. So we are trying to work to elevate sectoral transition actually from fossil-based, how we can move to the clean energy. And here we are trying several models and innovations to be implemented on ground level, which have a potential for scale and sustainability. We also work with relevant decision makers, institutions to equip their capacity on informed decision making. It may be SPCBs, PCBs, all regulators who are engaged in the process of supporting this mitigation and reducing exposure to air pollution as a part. And we are also engaging thoroughly with the citizens. So we basically would empower them in making and understanding and taking a call on better air quality for themselves, how they can contribute towards better air into their own area. So our overall purpose of this project is that how we can support NCAP's ambition to accelerate its ambition of cleaner air in the country actually, and to develop an ecosystem wherein there is a greater cooperation between government and non-government organizations, and there is a greater acceptance of innovations to move ahead at a larger scale. By in large, totally, if I would like to summarize the impact of CABH, we basically talk on establishing scalable and sustainable models and innovations for accelerating particulate matter reduction in the country. So some of the examples that we can talk about is that, yes, we are piloting modeling clean energy technology within the MSME sectors, where we are demonstrating 98% reduction in PM level 2.5 at this moment. We are working on improving the access to the LPGs, even though if you right now see in India, the access is almost 98, 99% in the country at this moment, but the usage is not to that level. So we are working on how we can improve access. Here we have been able to do the largest survey of distributors, and then we are also right now coming up with micro level solutions on this distribution. Another is that we are working with SPCBs, how we can improve their capacities to navigate legal instruments on air pollution. And this we are doing through our first ever national portal on VayuLex, what we call, where it is a platform which gives a chance to everybody to navigate, talk, discuss, and understand in detail what are the orders, compliance, and things in that. We are also working on solid waste management, where through our pilots, we are demonstrating 17% reduction in emissions if we are properly going to manage the waste. Similarly, in the mobility sector, we are working towards the more e-vehicles movement. So within our target, we have planned that at least 7,500 e-vehicles get translated, which would finally result in a reduction of 6.2 tons of PM 2.5 in Lucknow and Amritsar as a part of it. As a part of community engagement, yes, we are working with Clean Air Action Hubs. Now, basically, these Clean Air Action Hubs are informal groups of citizens who are interested in solving the problem of the air pollution in their region. And we empower them, and then they are making a coordinated effort with the respective UNDs to work on improving the condition there. We are working with the NCDC on strengthening the sentinel surveillance sites where we get data on the air quality and related diseases. And this we do through various things. One of them is capacity building of the sector, plus also piloting the operational issues on the ground level, how it can be enhanced, a part of it. As a part of this also, we are also working on adopting a kind of framework where we talk about how do these buildings, they adopt established protocols on monitoring and management of indoor air quality, and through the advanced healthy building design and retrofit. And this is one of the things that today we are going to also discuss a part of it actually. We are also working towards the self-regulatory monitoring regime at the construction sites with the potential to demonstrate 40% reduction in PM 2.5. So basically, as a part of it, we feel in innovating, integrating, and implementing for impact. And just to demonstrate these, a couple of examples. As I talked about construction sites, yes. So under CABH project, we have implemented first of its kind air quality monitoring network for construction sites. And this is basically to strengthen the self-regulation of polluting activities and promote clean construction practices by the constructors themselves in the place. Similarly, when we talk about evidence generation on health impact for exposure to air, so here we have developed standard operating procedures, guidelines, and also we are providing technical assistance to Madhya Pradesh and Bihar government for strengthening their surveillance mechanism on air pollution and related diseases. When we talk about about our participatory approach further, transition to clean cooking fuels. So we are exploring solutions on carbon credits, microfinance, grants as a business model to increase the affordability. So we are just designing those business models, how it can work in different parts of the country. As I informed earlier that yes, we have been suggesting reforms based on our LPG distribution system survey that we did. And then also on the clean cooking fuels, also our clean air action hubs, they are working in known attainment cities to improve the ambient and household air pollution mitigation efforts. And this whole exercise, all these citizens, they all are voluntary in nature, supported by CABH part of it. As I told we are doing some of the innovations at the ground level. So we have developed first of its kind natural gas furnace. The piece, that brass piece, the green piece that I showed you earlier, it has been the result of this only. And right now we are in the process of doing a patent of this, and this whole implementation in Muradabad is going ahead. Similarly, you can see a battery-powered variable heating solution. So this is one of the solutions that we are looking towards, stubble burning in areas like Delhi, especially in the winter season. So these are heated jacket apparels which can have a control on the temperature, inside temperature, and they are fitted with battery powers and they are worked. So we have piloting this with the security guards and other outdoor night workers to see this feasibility and how it takes away. Similarly, when we talk about, I talked about transition from fossil-based to the e-vehicles. So here we are working on towards diesel e-autos to the e-autos. Also, we are also trying to include women into this. So we have made 4 self-help groups, and here due to the efforts of whole CABH project, we have been able to get the government buy-in for 200 women auto drivers for driving these autos on that part. So we ran a campaign on Sarak Ke Sartaj here to influence those things. Other capacity building and operational support that you work through data and knowledge products. One is, yes, we are working strongly on decision support system with Thane government here. And here we are supporting the municipality in how this whole decision support system can be informed making or decision making in a part of it. I already talked about improving waste management system, but the model that we are adopting right now, at least in schools, is that we want to create a first zero waste audit intervention in the schools. So zero waste to schools plus zero waste wards also in that. Similarly, we are working on the framework for scaling healthy buildings, which are a part of now today's discussion, so that we can have good indoor air quality in place. So we look forward for building solutions to scale, and then once we have, we would like to institutionalize the best practices to move forward for the sustainability. So thank you, and thank you for your kind listening.
Thank you, OP. Before we move on to the expert sessions, let me set the context to today's dialogue. Let me begin with a thought-provoking trivia question to pique your interest. If anybody here can answer who said this quote, I'm certain that no air is so unwholesome as air in a closed room that has been often breathed and not changed. To give you a hint, it's from a famous American. You can use the chat box to answer. Okay, I will give the answer then. So it's Benjamin Franklin. Considering that we spend an increasing amount of time indoors, indoor air quality has become a topic of concern. As part of the CABH project, we have been conducting a study by monitoring air quality in indoor spaces. Here is an insight on carbon dioxide concentrations measured in 2 office buildings in Delhi. It was observed that there was a gradual increment in carbon dioxide concentration over time due to occupancy. We see that occupants of Office 1 were exposed to carbon dioxide concentration above the recommended threshold for about 13 hours of 13% of the office hours, and occupants in Office 2 for about 22% of the office hours. This indicates inadequate ventilation, and high levels of carbon dioxide are associated with drowsiness, headache, and overall reduction in comfort and productivity of occupants. Smart ventilation systems here can play a crucial role in managing IQ. A smart ventilation system can continually adjust itself to provide good indoor air quality while minimizing energy use, thermal discomfort, and noise. It adjusts ventilation rates in response to aspects such as occupancy, electricity grid needs, outdoor thermal and air quality conditions, direct sensing of contaminants. It can also provide information on indoor air quality, energy use, and any need for maintenance. The primary aim of employing a smart ventilation system is to enhance indoor air quality while optimizing energy consumption. Now, further, how do you evaluate indoor air quality in a building? Here are some approaches that one can look at. One is conducting an indoor air quality audit, which would involve a comprehensive inspection of a building's indoor environment, which will help in identifying the potential sources of indoor air pollution, deficiencies in ventilation systems, and other factors that affect IAQ. Another approach to evaluating indoor air quality is by continuous monitoring. This would involve real-time measurement and recording of some of the key indoor air quality parameters, and then drawing insights to develop interventions that can help enhance the quality of indoor air. These were examples of quantitative approaches. Now, a qualitative approach could be conducting an occupant survey. So this would involve gathering feedback from building occupants about their perceptions about indoor air quality and any related symptoms or concerns they may have. Our experts will share deeper insights on these topics today. Moving on to the next session, our next speaker is Dr. Jelle Laverge, who is an associate professor at Ghent University in the Building Physics Research Group of the Department of Architecture and Urban Planning. His research is focused on residential ventilation. He also serves as the operating agent of IEA-EBC Annex 86, a part-time attorney at law, and he is also a member of ISIQ, SRS, and ASHRAE. Dr. Laverge holds an MSc in Architectural Engineering, an ML in Fiscal Law, and a PhD in Engineering from Ghent University. He has also served as a scientific co-chair of BS 2021, the president of IA 2016, and a visiting scholar at the University of Texas, Austin. It is an absolute pleasure to have you on this dialogue, Dr. Jelle. Over to you.
Thank you. Thank you for the very kind introduction and for the very nice setting of the problem, let's say. So first of all, thank you for having me in this session. It's a great pleasure to talk to you about this topic that has been the focus of my research for, I would say, the last 15 years. And that is rating and designing smart ventilation systems for residential buildings. Before I go into the topic, I would like to say that indeed I'm representing, of course, my own research group at Ghent University, but also the whole team of IEA-EBC Annex 86, which involves 42 institutes from 20 different countries, which is working collaboratively for the last 3 years on this same topic. And also representing AIVC, which is another IEA-EBC annex that is focused on the dissemination of knowledge related to air infiltration and ventilation in buildings, and who is also partnering with Annex 86 to disseminate what we produce there. So as a first section, small part of the talk, I would like to go into what smart ventilation actually is. And this is where AIVC immediately comes in handy, because as part of the type of content that they produce, they have a publication series called VIPs, or Ventilation Information Papers. And one of those puts forward a definition for smart ventilation that is relatively long. The full definition is what you see on the left, but I would say the relevant part for this lecture is that smart ventilation is a process to continually adjust the ventilation system in time and optionally by location to provide desired IAQ benefits while minimizing energy consumption or some other parameter. So it's a control strategy for a ventilation system that allows to match the ventilation rate to the need at that particular moment, at that particular point in time. What does this mean? If we take a typical residential ventilation system, and here I'm referring to our Belgium standard, but because of course that's the one closest to me, but there are many other standards that have a similar strategy. The standard will say where you need to put ventilation components. For example, supply in the living spaces, who are marked here in blue. So that's the living room and the bedrooms. And then some kind of transfer device to let the air move from the living spaces to circulation spaces or wet spaces like kitchens, bathrooms, and toilets, where the air is exhausted, and then those wet spaces are here marked in red. And so for each of these components, the standard will typically say how to design them, what size they should be. And then also typical existing ventilation standards will then have a small mention like the clause 7 here, which I translated for you as supply or exhaust openings can be equipped with an automatic control system that functions based on air quality or wind pressure or CO2 or water vapor concentration. So it's very open, not very defined, and it creates a possibility to use the system designed by the standards as a smart ventilation system, but it doesn't really go into detail. So that's kind of the typical situation with existing standards and regulations. And that is then where our research comes in. Trying to understand how you can actually design these systems to give you an optimal result. And for that, we first of all need to understand, since smart ventilation tries to optimize the ventilation flow rate to the demand, what the actual flow rate in a building is. And as you can see here on the graph, where we try to measure it over a longer period of time, this can actually be very variable depending on the design of the system due to wind pressures, opening of windows, and so forth. And the amount of air, fresh air from outdoor that you're getting in a specific room, like the bedroom or the living room, can vary quite dramatically over time. But these measurements are very labor intensive. So using these to then learn how to design and optimize the design of a building is quite cumbersome, because, well, you first need to build it, then you need to do measurements. So that's not very useful as a design strategy. The next best thing is then to simulate this whole situation with the best available numerical models, which in case of airflow or CFD or computational fluid dynamics models, with which you can model the whole building, model the airflow, the wind around the building, and also the movement of the air inside all of the spaces. But similarly as with building and measuring, these models, although they're getting more manageable very fast, they're still very complicated to construct, and they take a whole lot of computational power to actually run and interpret. So typically what we do is try to understand the different processes that govern the exposure of people inside buildings to indoor air pollution and that govern the airflow, and come up with a reduced order, a simplified model that captures all of these relevant processes. And this is an image that I combined from different papers that are quite famous in the field, that somewhat summarize all of the more or less relevant processes. So emissions of pollutants in the buildings, air exchange through different means, interactions between different pollutants, occupant behavior, and so forth. So if we want to try to capture all of these processes, in my opinion, type of model that strikes a good balance between the required precision and feasibility are multi-zone airflow simulations models. There are many different ones. The most well-known are CONTAM from the US and COMIS from Europe. This is an example of CONTAM, where we translate the geometry of an apartment into a multi-zone model that models each space as one calculation node. So you get one concentration per space, and then it models all of the interactions, for example, connections between the outdoor and the indoor here, connections, emissions, sources, sinks, and so forth. So basically all of these interactions can be included in those models per space, and then you can connect all of the spaces in a dwelling. And important for what we're discussing today, you can also input or add what a ventilation system brings to this whole balance. And then, of course, you need to model all of the relevant parameters, about the ventilation system. When it's a smart ventilation system, that can be all of the smart controls. For example, it could be a control on the central fan if it's a mechanical system, or there could be dampers on vent holes or trickle vents, or programmable timers with some feedback, or sensors that govern or reposition some of these systems. Okay, so if we then try to apply this whole strategy of simulating with a multi-zone model to a typical building, this is the plan of a 3-story building, typical dwelling in Belgium, I would say, where the supply and exhaust spaces are marked as I explained when I was discussing the standard. And then we can use these models to really analyze what is going on in the building. And then we can see on the left side what we designed the components, the different components to do. So we were expecting 200 cubic meters per hour of supply, both on the ground floor and the second floor, and an exhaust of 150 meters cube per hour. And if we then do the simulation, we see a very different result where we get more supply on the bottom, but much less on the top floor. And of course, the mechanical component does what it is supposed to do. And if we then analyze what is going on, we can see that this is caused by the interaction of a stack effect, so temperature difference, that causes air to come in at the bottom and go out at the top, with the natural supply grids or trickle ventilators that are installed at these places. And then we have the exhaust system that pulls in air And so at the top floor, you can see that these two driving forces cancel each other out, which leads to very low airflow at that point. And so using this insight, which creates bad indoor air quality in these rooms on the top floor, which are typically bedrooms, we can adapt the design of the ventilation system and, for example, add additional exhaust locations or vent holes in each of the bedrooms, which then improves the under pressure that is generated by the system and overcomes the unwanted influence of the stack effect. So this is a way to improve use these models to improve the conception and the design of ventilation systems. Now, what can we then use, or how can we apply this to then rate specifically smart ventilation systems? Well, if we again look at this start situation, we can use it to model over time the exposure of people in this space to a specific pollutant. Lakshmi also already introduced the CO2 as a marker of indoor air quality. And then if we have this trace, we can identify the moments where the exposure is too high, and so the indoor air quality is not good, and we can try to adapt. And then we can do this analysis for different design options, here marked in the different lines in the graphs, and we can see that one will have a better or lower exposure to indoor air quality, but provide better but at a higher energy cost, or the vice versa. And I think this is a good point to trigger the first interactive question. So the first question is, do you think it is possible to get the best of both worlds, let's say, as Americans would say, have your cake and eat it? So can you achieve with smart ventilation better indoor air quality and energy savings at the same time? Okay, so I'm happy to see that many of you are quite positive, in the sense that you 2/3 of you agree that it may be possible to achieve better indoor air quality and energy savings at the same time using smart ventilation, and I agree. So this is what we then try to investigate. What is the potential of smart ventilation? And for that, we simulated, using these models that I just explained, a whole range of different possibilities, different sizing, different control strategies, and so forth. And this gave us this overview of the possible results, where you see on the x-axis the energy use, on the y-axis the exposure to, in this case, CO2. And from that, we selected the Pareto optimal solutions, so the ones that where there were no other solutions that had both a better indoor air quality and a better energy use. And that's the ones marked in circles here, that we can then compare different strategies one to another. And this is what you can see here. So the line marked with X's is the strategy, the best performance that we could achieve with with a constant flow ventilation system, so a system that does not have advanced controls. And then the line marked in circles is the best performance we could achieve with demand-controlled ventilation systems. And you can see that we, on average, achieve either a 30% reduction in energy use with the same exposure to, in this case, CO2, or vice versa, we achieve a reduction of 30 to 40% in exposure with the same energy use. So clearly, we are able to achieve better performance. So far, we've been talking about CO2 as an indicator because it's the most commonly used, but the definition that we were using stated that we would change the ventilation rate to achieve the desired IEQ benefits, and this triggers the question: what are these IEQ benefits that we're looking for? And this change is actually based on what type of rating that you're trying to do. There's three main areas where you want to do this comparison. It's when you're directly comparing design options for a specific building, so comparing one case to another. It's where you're trying to compare general solutions, so a type of system, for example, mechanical exhaust ventilation, comparing to a system by window opening, something like that. So general solutions. And then there's the case where you want to do that same thing, but then for a whole building stock, so on a policy level. And for that, typically you do not want to look at just one component of indoor air pollution, but there are many different indicators for indoor air quality. For example, on the graph I just showed, already I actually had two. I had the average exposure, which are the lines, but I also had the peak exposure. And you can see that for peak exposure, the potential benefit, there's still a benefit from using smart ventilation, but in percentage, the benefit is slightly lower between the dots and the X's. And so that triggers the question: which are the good indicators for indoor air quality to use, and what happens if you use different indicators in your assessment? And this was the topic of a PhD from La Rochelle University by Louis Conny, who compared on a given set of dwellings what the impact would be of using different indicators. This is a general overview, but if you're interested, definitely read the whole PhD. And this triggers for me a second question that I would like to pose to you. That is, what are, in your opinion, the correct or the measurements that you would need to use and simulate to rate and compare different ventilation systems? So what is, in your opinion, the indicator that should be measured to control smart ventilation systems? All right, so here we have a much wider distribution of answers. So CO2 is still the most popular. It's also in practice the most commonly used because it's quite easy to measure. But then we also see quite even distribution across all of the other suggestions that were made. And of course, as you can see in the list, there are still many others that are possible. And to go into that a bit, I want to introduce something that we are working on in the framework of a new European standard. That is that actually the answer to that question is not straightforward because there are many different options and you need to go through a whole process to identify what could be the relevant indicators and verifiers for your situation. And first is to define the high-level objective, and then from that go more specific through these different steps. And here I listed some of the potential answers to each of these steps that you could have when you're looking at indoor air quality in residential buildings. And I want to focus on health because, well, that's the general umbrella of the project that is hosting these breathing dialogues. And so one of the principles that you would like to achieve with your ventilation design is that you would like to avoid excessive impact on health And this could then be translated, for example, in the fact that you would like to limit the amount of harm to health that people are exposed to in the building. And then this would need to be translated into an indicator. And for that, within Annex 86, we updated the framework that was developed previously that uses DALI, or Disability Adjusted Life Years, which is a measure that tries to combine different impacts that exposure to indoor air pollution can have, both on the fact that you may prematurely die, so that's years of life lost, and also while you're alive, you can also have reduced quality of life due to disease, and those are the years lived with disease, and those are then added, and this forms the metric in DALI, or basically lost healthy life years, right? And so if we are using this metric, we can rank pollutants based on the harm that we expect that they will cause over the lifetime of the occupants. And the University of Nottingham made a very interesting study where they updated the best available data on different typical indoor air pollutants. And this is the order of pollutants of concern that they came up with. Note that the scale here on the y-axis is a logarithmic scale, so there's an order of magnitude difference between the different indications on the axis. And so PM, particulate matter, is clearly dominating the health impact, and then followed by nitrogen dioxide, formaldehyde, radon, and ozone. And all the other pollutants that they investigated, they looked at several dozen, form less than 1% of the total expected harm together. So we use this framework to then include in our design approach, and also came up with a variation of the DALI that is more adapted to the processing of the results from dynamic simulations, which we call the dynamic DALI or time-resolved DALI. And so we can use the same approach as I showed you earlier. We can look for a reference system and then simulate different variations and see if they are better in terms of exposure, and so DALIs and energy use. And we can also use this to create different allowable thresholds. For example, we could set a maximum level of harm that we think is acceptable in buildings. And then we can see, of course, when we look at a reference system that runs at very low flow rates, we will probably not achieve this maximum harm level. Or looking at the fact that improving indoor air quality also has a cost in terms of energy, we could define a maximum trade-off, let's say, between indoor air quality and harm that is caused, where we allow a lower exposure if it uses more energy. And this framework can also be used. So far, we've been talking about smart ventilation. In the annex, we look also at other ways of managing indoor air quality, for example, adding air cleaners. And so we also extend our assessment framework to include the benefits that are achieved by, for example, adding air cleaning, where in a situation with low ventilation, if you add an air cleaner, the amount of DALIs that you expect because you remove the PM will be much lower. And so you can compare a situation with low ventilation and an air cleaner to an equivalent situation with a much higher ventilation rate, and therefore try to use this framework to make rational decisions on which technologies to use. One step further, and that's the last thing I want to mention, is that you can add all of these different ways of assessing ventilation systems, so based on health, based on impact on performance of people in the building, cost, and so forth. And what we propose there is a method where we monetize all of these impacts. For example, the impact on productivity, we will then translate into a dollar amount because people are less productive, and therefore the company that employs them in the building loses money. And then we can add all of these up. This is a result of different simulations for that. But in general, what we see there is that sick building syndrome symptoms, so symptoms like headaches, dry eyes, and so forth, are much more prevalent than real health problems, problems that cause long-term disease, let's say. And because of this higher frequency and the impact they have on productivity, the total costs of those aspects are actually much bigger even than the direct health impacts. And so to close, I would like to just give you a small peek of the work that we're just starting, where that opens an avenue to even more, I think, improvement of performance. And that is, we're now looking into what the part of the definition that I skipped over, namely that we are not only adjusting the flow rate of the ventilation in time, but also by location, in a sense that so far we're only looked at systems where the route of the flow through the building is fixed. It comes in the living spaces and goes out in the exhaust spaces, in the wet spaces. What we're now starting is a project where we have bidirectional flow elements that allow us to constantly, based on wind and conditions in the building and occupancy, adjust the route of the air through the building to really provide the air at the moment and the location where it is best suited to reduce the exposure of the occupants. And if this sounds interesting to you, then I'm happy to tell you more about it in the future at a conference or a webinar. So thank you very much. And with that, I will close.
Thank you, Dr. Jelle, for sharing your research and experience on smart ventilation systems and their rating. Our next speaker is Dr. Chandra Sekhar, who is a professor and program director at National University of Singapore in the Department of Built Environment, College of Design and Engineering. He is a fellow of ASHRAE, ISIAQ, and Engineers Australia. His research is focused on thermal comfort, ventilation and indoor air quality, bedroom IEQ and sleep quality, airborne infection control, resilient and energy-efficient HVAC systems, and building energy management. He currently serves as ASHRAE Vice President and Board Member, ASHRAE Distinguished Lecturer, and continues to serve the Society in various other capacities. Dr. Sekhar holds a BE in Mechanical Engineering from MNIT, Jaipur, and a PhD in Mechanical Engineering from the University of Adelaide, Australia. Dr. Sekhar, it's an honor to have you on this dialogue today. Over to you.
Thank you so much, Lakshmi. So I think let me get started by first thanking for inviting me to be part of this webinar. It is indeed my honor and pleasure to be part of this panel today to talk about, I think, a very important topic and subject that is very close to a lot of us. Certainly, it is something that is very much part of what I have been involved in over the decades, so to speak. So it is with much interest and probably I'm also looking forward to some dialogue and interaction after the presentations proper. So I actually titled this Indoor Air Quality Audit in Buildings. So it's a kind of a nice segue to this part after what Dr. Jelle Laverge spoke about. I will be focusing more so on how we can measure, what we can measure, and this whole question about the kind of connection between the system and the spaces where we do these measurements. So I think that is very important. That is, in fact, one of the fundamental requirements, at least from our perspective in our group. So let me proceed further. The objectives are listed here. I will be introducing to you a certain methodology that we've been using for the last 3+ decades. We have this as part of our research, as part of some of the work that we do in the industry, and it is also very much part of our curriculum at the graduate programs, where we do get the students to actually carry out an audit methodology in a real building so that they get a hang of what is involved in indoor air quality measurements. And I'll also share with you some of the case studies that we have done so you get a handle on what's being measured and how they are presented. So maybe before we get started, some fundamentals in terms of indoor air quality. We always talk about something that we refer to as a good starting point. So we say that if there is a problem in the building, in the space, just get rid of the problem. Contaminant source, remove the source. A lot of times we can do that, but there are times and situations where you can't do that. For instance, we ourselves are source of contaminants in the building. We emit carbon dioxide, for one, and we also result in a lot of other contaminants that get increased or get part of the contaminant concentration profiles. You can't ask all the people to leave. So that's something that we have to work with or live with in terms of the source, but we can address what happens to the people in terms of the exposure. So we can do some other things. So when it comes to exposure control, we can use ways and means to minimize the exposure of the contaminants to the occupants in the building. So here ventilation is often used. I'm sure all of you can relate to that. It's using outdoor air to dilute the contaminants from the occupied space. In here, 3 things are important: quality of outdoor air, the quantity of outdoor air that's brought in, and also the room air distribution. So the room air distribution results in how the air is moved through the occupied space in diluting the contaminants. And herein, there is an important characteristic that we often try to measure and have a good understanding of, what is called the ventilation effectiveness. Sometimes it's called the air exchange effectiveness or some other related term. The whole idea is we want to get rid of the indoor contaminants, dilute the contaminant so that the exposure to the occupants is sort of managed or minimized. So the indoor air quality audit as a methodology is part of what we have been doing in terms of, say, an indoor air quality management plan, if you like. So we say that one would have to do an audit measurements so that you can establish the status of indoor air quality in the building as is to begin with. And then you can identify strategies for improving the indoor air quality. And that can then be part of an integrated indoor air quality management plan that can then be set in place in the building for years to come in the future. So it's kind of similar to what, most of us are familiar with, as energy audit, something similar to that. So you do a set of measurements, find out where the building is currently in terms of the air quality or the contaminant levels, and find what strategies are possible. Some of them could be simple strategies, some of them could be more capital intensive, and that would then have to be somehow featured in or factored in as part of the improvements in the building over a period of time. So I will very quickly go through this framework, as we call it, the indoor air quality audit methodology framework. So we have generic stages. Just like as any other audit approach, you'd want to see what the building is about, what kind of building is it, look at the drawings, look at the functional characteristics, the functional spaces, who are the users, what kind of functions happen, because sometimes the activities and the functions in a building will result or lead to certain types of contaminants, and that could be perhaps an opportunity to address it from a source control perspective, or one may have to deal with it differently. Maybe there's a local control, a local exhaust or something along those lines. So looking at the generic stages, investigating what the issues are, these are all part of what the initial steps in an audit methodology is. What is more critical, I think, as part of the initial steps, also a simple walkthrough of the building. I don't think I would be able to say anything about any building just looking at the drawings, because I would always want to do a walkthrough. When you are in the spaces of the building, when you are in a building, you get a better hang of what's happening to the air. I always tell my students, I tell myself all the time, as long as we are not sort of having some kind of cold or a infection or anything like that, our nose is a very good sensor. Use it. Let's use it. So walk through the space, see what you feel. Sometimes you pick up things that are not so obvious, even from a technical evaluation, but you think, oh, that might be a potential source of contamination that we may want to quantify or even maybe substantiate through some measurements. So characterization of the environment is very important as part of the walkthrough and trying to come up with a plan to do the measurements. Now, why are we required, or why do we think measurements are important? Is because unless you measure, you wouldn't know what's happening in the building, and you wouldn't have a handle on what you want to do to improve the situation in the building. So before I go to the data collection part, focusing again on the characterization of environment, I would want to highlight an important aspect of this particular talk that I'm giving. We need to be able to relate the spaces to the air conditioning and air distribution system. The methodology I'm sharing with you is more so for commercial buildings, large buildings, central air-conditioned buildings. So we want to be able to relate to buildings, but building spaces to the system that serves the building. So air handling units, or if there are fan coil units, or if there are pre-treated AHUs that are factored into the building design and operation, all of that we need to understand, because remember, the contaminant level in a space and its exposure to the occupants is inevitably a function of what the air in that space is doing. So if we have an air-conditioned environment, things are happening through a mechanically operated system, what we call a forced convection air distribution system. That is fundamental to what I will now talk about as the rest of the methodology and the framework. Then comes the data collection part. So we want to be able to measure the contaminant levels in different spaces. A few important things: occupied zone, occupant height. There isn't much point in measuring 3 meters away from the floor of the building, where a person is never going to be actually present. And there's also not much of a point in measuring right at the floor level, because you are not going to be inhaling the air from there. So one important aspect to remember here is, let's measure where it matters the most, where people are, where they're going to be inhaling the air from, and that's what is important for exposure control. Once we have the different types of data measured, I will show you what kind of data we measure. Then we need to be able to do a reasonable analysis with that. Sometimes it may just be, what do the standards tell us for some of those contaminants? Can we do a comparison with the standard values and see, are we falling short? Is it good? Is it too high? Then what kind of solutions can then emerge based on what the building measurements are? So the data analysis then leads us to trying to find some causal factor. If the CO2 levels are exceedingly high, then perhaps there isn't much of a ventilation occurring in that space. A simple causal kind of contributing factor that we can identify. Once we know what is causing the contamination to be high, or concentration levels to really go beyond permissible limits, then we can identify some mitigation solutions. So I've been talking some of this data collection part. So here are the things that we measure: the thermal parameters, thermal comfort parameters, that is. Then we have the particulate matter measurements, biological sampling, chemical measurements, ventilation characteristics, not often and not commonly measured, but we do it as part of our methodology to understand the link between the system and the contaminant level in the space. And we always tell our students, our clients, we tell ourselves, no objective measurements alone is going to be enough. We've got to talk to people. Now, let's face it, we might have the most fantastic systems and the and all the air distribution in the place in the building. But if the occupants don't like it, and if they say, look, I'm still experiencing some issues, we got to be able to address that. So questionnaire, survey, occupant feedback is an integral part of the IAQ audit methodology that we are talking about. Then when it comes to analysis, as I said, we look at existing standards, statistical analysis of what's going on, all that is critical. Then we can compare with other, our own understanding of solution that might fit in to improve the situation. Then we can find out what works best for that particular building. Now, the key takeaway here is, key to good IAQ evaluation, let's not forget the system zone concept. We can't just measure the contaminant levels and not be able to relate it to the system, because then we wouldn't know how much ventilation is being provided, is ventilation being provided in the first place, all those sort of intricacies. We do the audit methodology or indoor air quality audit also to establish the status of the IAQ as is at this point in time. And then we can find ways and means to improve further. And ventilation performance measurement is almost an integral part of it. Lakshmi, at this stage, can we go to this poll 1?
Yes, sure.
Thank you. So thermal comfort acceptability and indoor air quality acceptability in an indoor environment, is there any correlation? Right, so that's very heartening for me to note. We have an audience that's almost 80% say that yes, they are correlated. Now, let me show you what our research in the past has shown us. It is indeed correlated. Here is the studies from about 5 buildings that we did with multiple spaces, locations, almost some 90 over locations. Left y-axis is the indoor air quality acceptability, thermal comfort on the x-axis. You can see that when people perceive the thermal comfort to be good, they also find the IAQ to be good, and vice versa. When it is not so comfortable thermally, they also find the acceptability on IAQ not so comfortable. So that's very clear. They are indeed correlated. Relate to the fact that we experienced in a lot of buildings when we go there, if the thermal comfort is good, we almost inevitably would say the air quality is good. At least we won't complain about the air quality straight away. Another observation that we did from our research measurements in the field, indoor air quality acceptability with stuffiness, with the quality of the freshness, whether it is fresh or stuffy. Again, when people feel that the environment is fresh, the air is fresh, the acceptability increases or improves. That I think goes without saying as well. So this is just a kind of something that gets substantiated through questionnaire analysis and surveys that people respond to. Now, I'm just going to very quickly take you through some of the measurements that we normally do in indoor air quality audit. There's chemical measurements, biological measurements, physical measurements. The chemical measurements here is a continuous measurement of carbon dioxide in a typical, this is an office building that we've done in the past. And you can see that the levels vary from about 400 plus, which is very close to the ambient level. The outdoor level goes up to 800 dips. That's lunchtime. And then it increases. And when people go home, it comes down. So this is a very clear trend. So there's Monday, Tuesday, Wednesday, Thursday, Friday. And those days we were also working half a day on Saturday, and that's Sunday, and the next day starts. So we always believe that continuous monitoring is very useful because it tells us a time trend of what's happening in the space. And of course, when it comes to chemicals, besides carbon dioxide, we also measure total volatile organic compounds, formaldehyde, carbon monoxide as well. How about biological contaminants? This is again something that we have been doing for a long time, and it's a kind of a rough indication of the level of hygiene in the space. So if you have bacterial contamination, for instance, colony forming units per meter cube, then we typically look at something like 500-600 CFU per meter cube as a sort of a level based on which we can draw some generic inferences. This is not going to be too definitive because you need to go and look at what species of the bacterial contamination exists. But that's going too detailed, maybe not so easy to do this analysis, measurement analysis. So we say get a general idea about what the bacterial contamination is. And here is something, these are all measured data from our studies. And we find that there are some buildings where it is reasonable and others it does exceed. So obviously there would be some relationship to maybe occupancy, visitors, increased visitor presence in the place, food being eaten inside the building space. Sometimes it could be outside sources as well. These are all the possibilities of the biological contaminants to be high. Another poll, let's do this. Room air distribution is an important factor in controlling contaminant exposure to occupants. Almost unanimous. Thank you so much. So it does have an impact, correct? Air distribution does have an impact on the exposure to the occupants. So here are the reasons, the factors that affect the ventilation performance, the space layout, the amount of outdoor air that we bring in, the supply diffusers, the return grills, and then the indoor airflow pattern itself. There could be short circuiting between supply diffusers and the return grill. If it is like a unidirectional flow, like a piston flow, you supply at one end and then it moves through the space and it pulled out of the other side, which is a better way of doing it. Perfect mixing. This is what we find in most building designs. We call it the mixing ventilation design concept, where the air supply through the diffuser completely mixes in the space. So the air quality is the same everywhere. And at this juncture, I would just want you to ponder over this question. Why would I want the air quality to be the same in my breathing zone and 2 meters above me and anywhere else where I'm not going to be there? More specifically, where my face and my nose is not going to be there, because the inhalation is the result that is going to lead to my exposure of any contaminants. So the air that I inhale from in that zone, that's the most important part. So we have moved quite significantly in terms of advocating the fact that the breathing zone, the individual zone of a person in a building, in a space, is the most critical space. So let's rethink our old strategy of making the air quality everywhere in the building, in the volume of space the same. Can we focus on the breathing zone and what the occupants need? So here, when we come to ventilation characteristics and ventilation measurements, we use tracer gas measurements. In the past, we have used sulfur hexafluoride. It's a very good tracer gas, but then now it's almost not usable. We don't use it anymore for general tracer gas measurements, because SF6 is a global warming gas, so it's got a very high ODP and also has a high global warming potential. So we don't use it anymore. But in the past, when we used it, of course, we can use other tracer gases now, including say N2O or even CO2. But then there are nuances in terms of how we can use them. It gives us the ability to measure the age of air, how long an air, the molecule of air that we take in as clean air spends in the volume of space. And using that age of air measurements, we can compute a lot of things like the air change per hour in a space, the air exchange effectiveness. These are all some details which I don't have the time to go into it, but that's what a simple, well, it's not really a simple, that's what a detailed tracer gas measurement will tell us. I have this slide to give you a sense of what kind of analysis can be done with these concentration measurements of tracer gas. We are talking about an index called the contaminant removal effectiveness. The term itself is self-explanatory. One can look at the word contaminant removal, how effective it is, and that's what this index is all about. And here I show you a diagram, supply air, concentration of that tracer here, concentration of that somewhere in the occupied space, concentration at any point in the room, concentration of that in the exhaust. These are the key, and concentration in the inhalation zone. That is critical, right? All of these are different different concentration levels that we can measure. Look at this CRE, or the contaminant removal effectiveness. The numerator is the same, which is basically CE minus CS, supply concentration, or other exhaust minus supply concentration. This is going to be high because picking up all the contaminants from here. And then depending on where you're looking at this point, this space, this location in the space, that's contaminant removal effectiveness at the occupied space anyway. And this is at any point. And this is the most critical one. Contaminant removal effectiveness of the exposure at the inhalation zone. So I would be more interested in measuring or computing this value because that's critical from the perspective of what the occupant is being exposed to. Air change per hour, I mentioned that we can do the tracer gas, we can dose a certain amount of tracer, and then we can stop that gas being dosed and let it decay. And the decay is going to occur because there is ventilation air being brought in is going to dilute that gas. And we can do a simple plot of y-axis. It's a semi-logarithmic plot. This is a logarithmic scale, and this is a time scale. Simply put, is the log of C naught minus C1 divided by delta T. That's the air change per hour. It's as simple as that once we do the tracer gas measurement. Once we have the ACH, we can compute all the other parameters, like how much does that translate to in terms of the outdoor air ventilation rate. The air exchange effectiveness, I mentioned to you about the age of air measurement, which again comes from these tracer gas measurements. We basically have these three almost like a generally accepted, or actually it's theoretically substantiated as well. If it's a perfectly mixed air, the AEE is 1 because the air quality everywhere is 1. Think about it in that kind of a context. When the air exchange effectiveness, say 2, is like a perfect displacement flow. The cleanest, the youngest or the cleanest air enters the occupied zone first, the breathing zone first, and then as it goes through the space, it picks up contaminants, and then that's why a displacement flow or even something like a personalized ventilation flow will have a higher value in terms of the air exchange effectiveness. Then these two terms, sort of situations, when it is less than 1, there's short circuiting. Short circuiting is the time when the supply air straight away goes into the return or exhaust grill because the airflow pattern is impacting that kind of flow, which is not a good thing to happen in the space. But if we measure and we see that's what it is, we can do something about it. And we would also a lot of times know that that's what is happening because there could be something like a stagnation zone, and we might feel that the air movement is not there. It's kind of stuffy. So these measurements help us to substantiate those sort of things. Now, this is a summary of what we did when we did this 9-building study some few years back. There is, you can do in situ measurements, but there's significant variations in the measured ACH value because the real buildings in the field, you can't really control a lot of things, but that's exactly what it is. You're measuring what the building is actually going through. Some buildings do have short circuiting issues. There are stagnation zones, and we can fix them by doing kind of an audit methodology. But then we got to be able to link it to the air handling unit. The system zone concept becomes extremely important. The air exchange effectiveness values, they're generally, in our studies, they are indicative of well-mixed flow patterns, but that's not surprising. That's what the buildings have been designed for. But when we do have buildings that are designed differently, we get different measurements. I'll show you in a bit what I mean by that. I just want to very quickly go through a couple of case studies here. This is a grant that we got about 10 years ago to do to study a new type of system that we are working on. And here is something that you see here, a large building space, almost like 2,500 square meters, a lot of open plan spaces and several individual occupied zones, individual rooms. So these places, 1, 2, 3, 4, this is where we did the measurements. And this is how we would get continuous monitoring. Here is the measurements of carbon dioxide. Again, Monday, Tuesday, Wednesday, Thursday, Friday. By this time, we were not really having Saturday operating hours kind of thing. So weekend is very low, almost like back to the ambient level. And this is the measurement of the TVOC on the top. Again, during the occupied time, it will be low, but nighttime, it builds up from the contaminants released out gas from the building space because there is no air movement, there's no ventilation, it builds up. But the next morning when the AHU turns on, very quickly it comes down. So very nicely, we'll be able to see the trend of how the buildup occurs in the night. When the system comes in, the whole thing drops off. So these are the occupied hours in the day where the levels are quite manageable, very, very, very much within the limit values. Carbon monoxide has never been an issue in our buildings here in Singapore because we don't have any sources of combustion inside the building. Temperature and humidity, we measure these as well. Again, the idea is when we do continuous monitoring, we get a time trend of what's happening in the space. So here is temperature profile changing over time. 24-hour on a given daily basis, and then we do it for say 7 days, it certainly gives us a good picture of what's happening in the building. I spoke to you just shortly, a short while ago, about different types of air conditioning or air distribution system. This is a place where on the right-hand side is conventional ceiling supply mixing ventilation, and we were studying that for ventilation measurements. And on the left-hand side, two types of configurations. This part is basically displacement ventilation air terminal devices, and this part on the right is underfloor, combined with these are the points, the green ones, where we have personalized ventilation. That means I have a ventilation device coming right in front of me. It releases clean air or outdoor air straight into my breathing zone. So what do our expectation will be, these two on the left-hand side should have a higher air exchange effectiveness, and that's exactly what we measured. Look at these, the green zones here. These are all with, say, the personalized ventilation with underflow system or the displacement ventilation system, where the values are high, much higher than certainly the mixing ventilation that on the right-hand side is showing us about 1. That's what I said. Mixing ventilation is 1. When we have air exchange effectiveness of orders of 1.4 or 1.6, that means that there's something different that's happening, something good that's happening, and that can be associated with the clean air reaching the breathing zone first, and then helping to dilute the contaminants better, so it's more effective. My last topic that I wanted to address here, it's this like tying in with what Jelle was talking about, residential buildings. I've been involved with some residential building measurements as well. So this is in an air-conditioned split system type air-conditioned apartment in a tropical building. I'm sure there are so many of these applications in India as well. And this is a master bedroom. That's where the measurements were done, a split system unit. I actually had a poll question, but I don't have the time to go into that. Let me show you the results. Here you see, when there are 3 people, 2 adults and a child sleeping in the bedroom, master bedroom, the CO2 levels goes as high as almost 2,800, 3,000 ppm. Not surprising, split system units don't bring in ventilation. They don't bring in outdoor air. They just cool. Now, this is again, thermally we are comfortable, and then we accept the air quality as well, perceived air quality. But the real air quality is what you're seeing here. The CO2 level high means that the other contaminants are also high. We are exposed to it, but we think I'm thermally comfortable. Maybe my air quality is also okay. But the actual air quality is a different story. However, in this experiment, in this study, we had the ability to use an exhaust fan in the bathroom. The moment we turn it on, quickly comes down. So again, airflow patterns, air distribution, how we bring in clean air or ventilation air into the space, it's so critical. System zone, again, it goes back to the system zone concept that I mentioned for the commercial building application. So here is another example for the residential building situation. So future of the built environment, if we say there are all kinds of buildings, different types of buildings, we want to have good ventilation. Cities, communities, buildings, energy, sustainability, zero energy building. This is going to be the conversation world over. So things like good ventilation systems, we need to be able to monitor it, measure it, and where we have issues, we have to fix it. Final words, what I shared with you, an indoor air quality audit based on a system zone concept, some case studies related to the contaminants that we can measure, the parameters, ventilation characteristics, and what the human response is all related to that. And finally, we have to envision a future where the indoor air quality in the buildings or the built environment in general will be almost like an automatic process. It's going to be there. Everyone needs to be aware of it. We need to have systems that can do it continuously. And I think what Jelle shared about the smart ventilation is definitely part of this discussion that we are having, so that things can be more systematic, more continuous, more automated. And we know that we're walking into a space which can and will provide good indoor air quality. And with that, I thank you again for your attention. And once again, thank the organizers for inviting me to be part of this panel. And I think I'll pass the screen back to Lakshmi.
Thank you, Dr. Sekhar. That was a very insightful session on indoor air quality audits and our perception about indoor air quality as well. I would like to now open this floor for a discussion with our experts, Dr. Jelle and Dr. Sekhar. I would like to welcome Nidhi Gupta to kindly moderate this session. So over to you, Nidhi.
Thank you, Lakshmi. And thank you. It was like a knowledge-packed back-to-back session with both of you. I know we've shot over time, but I mean, just in a summary, Jelle, you covered, how ventilation systems can be designed, starting with, tools that can be used to improve them, whether it be modeling, moving on to the benefits and what would be the desired IAQ benefits, what are we actually trying to rate, right? And what would be the possible indicators for smart ventilation system, looking at then moving on the conversation to limiting harm. Maybe that is the possible indicator, the trigger. She showed an example of PM being one of the dominant indicators of harm. And then looking at, okay, health problems and cost models. How do we, the way we talk about right now is looking at IAQ and energy efficiency. Maybe we need to also bring in the aspect of cost of health as well in this conversation. And then we moved on to see that, okay, what's in there in the future, and we had a slight glimpse of that. With Dr. Chandra Sekhar, we started off moving from source control to exposure control, the methodology of IAQ. And so you spoke to the key questions at each stage in the framework, which need to be looked at when we are looking at IAQ audit. And that was very important. Where do you measure? What do you measure? At what point is it important? Where does the data analysis lead us to? What are the causal factors for high concentration? Questioning that. Setting our perception about, how occupant behaviors and the correlations in what is perceived and what is actually there. And that's why hence data and displaying data starts becoming very, very important. And you also showcased a couple of studies and bringing in, I think the important thing of the local air quality index, right, with the contaminant removal effectiveness. That was a very interesting aspect. So considering the paucity of time, I'm going to ask maybe just one or two questions for each of you. Dr. Jelle, I'd like to hear from you. Now that you are working with respect to smart ventilations and you're looking at ratings, are there any examples of putting these into standards and regulations to enable that to happen? And also, maybe a follow-up to that would also be, you brought up the aspect about, how we are looking at costs, and we need to bring the angle of health back into it. Are there any studies which have looked at that, looked at the whole total cost of energy, of IAQ impacts from a health perspective? And can you shed some light on these two aspects?
Sure. So to go into the first question you asked, the one related to regulations and standards, there are some existing regulations and local standards that include possibilities to have smart ventilation systems, mainly in Northwestern Europe. So we have one in France, one in Belgium, one in Ireland, one in the Netherlands. That's about it. Also, Spain and Portugal are working on or have something. The main move that is going on that enables thinking about smart ventilation, but also other kinds of smart IAQ management is moving towards performance-based standards. So many standards today are prescriptive. They say, like I showed, which components to have where and how to size them. I really feel that it's a good idea to create an opening in standards to also go for a performance-based route. So where you define the targets that you want to reach in terms of pollution level and exposure. And then you provide freedom as to how you do that to the designer. But then, of course, and that is where the link with Chandra's lecture is very important. A very important part of setting up such a framework is that not only do you provide an opportunity to come up with a design that achieves these performances, but also include a part that checks if those performances are then met in reality through an audit or a verification with a measurement. And then in terms of the monetization or the cost of these things, yes, there are some studies on that. There's an older study from France that looked at the macro level. So try to calculate the society level cost of exposure to bad indoor air quality. There's a more recent study that does a similar thing for China. For different regions in China, they come to relatively similar conclusions that it's a few percent of GDP actually that goes to bad indoor air quality or to treatment for the consequences of bad indoor air quality. And then in our own research, we and that's the graph that I showed. We try to modify this framework to move it from society level to the individual design decision of a building. And there we see, for example, that and this as a rough approximation is also already for a few years in the analysis of I think the US Green Building Standard, that when you look at the cost breakdown of a building, the energy use is 1%, the cost of the building itself is 10%, and the next 90% is the cost of the people working in a building, well, non-residential building then, of course. So you immediately feel that you would have to have an enormous impact on the energy use to offset a very small impact on productivity. And this is also what our numbers tell us. The total cost of bad indoor air quality in buildings is around a few thousand euros per person per year. So if you translate this into energy cost and investment cost, it's clear that investing in improving indoor air quality has a very short payback period. Okay. So yeah, I think that's a relatively short answer to your double question, but I hope it covers what you
yeah. Okay. So Chandrasekhar, Doctor, I do see a couple of questions on which have been asked by our participants, and maybe I take those for you. So okay. I think one of them is coming from the fact that in India you have a rising cooling load, you have you also have impacts related to outdoor air pollution, and how do you maintain indoor air quality, considering both the outdoor and the exaggerated cooling loads when you can't get outside fresh air. So how do you strike a balance between indoor air quality and energy requirements of a building? Is I think that's where the question is also leading.
I think the simple response is we need another webinar for that. I appreciate the question. These are issues and challenges. What I've presented is about a general methodology and framework that needs to be adapted to different situations. Very quick response. I'm fully aware of the high PM 2.5 levels in the Indian context. So simply opening the windows or simply bringing the outdoor air without filtration is not a solution. So we do work in an area in that space as well in our group, where we say that without having to even use air conditioning, if you have to provide ventilation to get outdoor air into the, say, the living room or the bedrooms or whatever, you need to address it at the building interface. So at the window panel, or maybe at the building, at the wall of the living room or bedroom or whatever, you need to have something like what we call a fan filter unit. So you basically have a fan and a filter that is high grade filter. A MERV 14 sort of filter is what, or HEPA filter, even better. High efficiency particulate matter, particulate arrestance filter, that sort of a filter would be necessary. You have to remove the contaminants before it comes in. You remember in my slide I said quality, quantity, and air distribution. So the question being asked is about quality. Yes, we have to address it. But then there are details, there are ways by which it can be done. And it is very unique to situations like where the outdoor air is very polluted. So again, the specifics can be discussed later, but that would be the response. You can't just bring the air without filtering it.
Okay. Thank you. So if just to for both of you, maybe one key takeaway or one message that you would like to convey to the audience or the participants today. Maybe Dr. Jelle go first and then Dr. Chandra Sekhar. One key message or...
One, I try to formulate it concisely, but as you said, this was a lot of information in a short period of time. I think a key message is don't be afraid of the complexity. It seems very complex, but actually your phone or your car is much more complex still, and still we're comfortable using it. And I think this is something we need to move towards in terms of indoor air quality, that we make the technologies that are able to address it easily accessible for everyone to use.
Thank you, Dr. Jelle. Over to you, Dr. Chandra.
Okay. I mean, this is probably at a very high level. I will follow on with what Jelle has just said. It may appear to be complex, but I think there are a lot of studies that have been done to kind of, solve the problem or solve the mystery, so to speak. So it is no longer a mystery. It is no longer, I can't do anything about it. In fact, we can do a lot about it. Education and awareness is the first thing, which is probably part of what we are discussing here. Once we know what the problem is, I'm actually heartened by the questions in the QA box, and I'm happy to even respond outside this webinar, because if you think there's a opportunity for that to be disseminated, I'm more than happy to do that. That's the kind of thinking. We know there is a problem. What can we do about it? With the thinking that, yes, we can do something about it. Sometimes some of these mitigation solutions are not too complicated, and they need not be too costly as well. They could be very simple strategies, but then done in the right way with the right focus. I'm sure there are ways and means to handle that. And also go on to add that just on the measurement part, since the pandemic, I think what has really become very commonplace and very prevalent in most countries and with most end users, like individuals, like occupants in the building, they have been able to measure carbon dioxide as one simple measurement of a parameter that they can relate to. If the CO2 level is very high in a building, maybe I should think twice before entering that building. But that's becoming like I have my own challenges, but at the same time I also have my own expectations and requirements. So these things are becoming more and more commonplace. People are articulating that I want to be in a building where the air quality is good. If you don't provide that, I also have a way of establishing whether it is good, acceptable, or not. So I think people are beginning to play an active role in the air quality because they know it matters, it affects them. It's about their comfort, health, and well-being. And we always have to remember, we spend 90% of our time indoors, and we roughly sleep for about a third of our life, both of which are very significant.
Thank you, Dr. Chandra Sekhar, and thank you for the offer of, we'll share these questions both with you and Jelle. Jelle, thank you for answering one or two of the questions already. And we'll share this back with the participants. For the participants, in case you have more questions, please feel free to reach out to us and we will pass them on to the speakers. I will hand this over back now to Lakshmi. Thank you, Dr. Jelle. Thank you, Dr. Chandra Sekhar.
Thank you. Pleasure.
Thank you, Nidhi. That was a really enriching discussion, and with all the insights that we have today, the better understanding on indoor air quality audits and smart ventilation systems, we can now identify opportunities to implement these best practices so that we design and operate buildings with good IAQ. Before we conclude today's session, I want to express our warmest thanks on behalf of the entire CABH team to our experts, Dr. Jelle Laverge and Dr. Chandra Sekhar, for joining us today and sharing your insights and research and expertise on the subjects. To all our participants who have joined us today, thank you for your active engagement and questions. Stay tuned for our next dialogue on our social media platforms, which will be around mid-June. With that, we bring this webinar to a close. Thank you, everyone.